Hello, I'm Aalok Sharma Kafle, and today me along with my friends Ademola and Zone we're presenting vulnerability assessment of nitrate contamination in Gulf Coast Aquifer, Texas. As mentioned in the title, our area of interest is Gulf Coast Aquifer that lies in the southeast part of the Texas, as you can see in this map here. And the right side of the area is completely engulfed by the Gulf of Mexico. So our conceptual model for this project is the presence of nitrate in the soil and how that happens. So there can be various sources of nitrate. Number one being the nitrogen fertilizers used by the farmers to grow on their agricultural land. It can also come in the form of landfill pollutions, manures, industrial pollutions, or residential pollutions, or leaking. So all of these sources, when they are in the contact with the soil and when they're helped by the precipitation, they infiltrate into the soil and can be in the form of ammonium nitrate or nitrite. Ammonium and nitrite, when they are in the enough matter, plants materials also absorb it, but when in excess, they leach into the soil, or when there is a sand presence, they reach into the groundwater as well. So the number one thing we need to predict the amount of nitrate in the soil is the nitrate data. For that, we went into Texas Water Development Board's groundwater database and we looked for the nitrate nitrogen parameter. And to not get very old data, we put a cutoff of 1980, so we needed wells that had at least one nitrate measurement after 1980 and had at least one well depth measurement after 1980 so that we can use it as an independent parameter when we are predicting nitrate later on. So the first thing we did was we plotted nitrate with well depth to see their relation. So as you can see here, well depth is in the x-axis, and as the well depth increases, the presence of nitrate in the water is decreasing. So to accurately show the data, we removed all the wells beyond 1,000 feet, and by doing that we have 1,889 wells remaining that we will use on the prediction model. And one of the data we plan on using on our prediction model is percentage impervious that we got from MRLC consortium's data. As you can see in the graph here, black to red means increasing order of percentage impervious, and we extracted the value for the each well locations. So to continue, I want to call my friends over.
All right, I am Deseyi John, and for this project, I worked on the precipitation data and the coastline, the distance of the well from the coastline. So I'll start with the precipitation data. I was able to get this data from the President Oregon State website, and I was able to get a 30-year number data from 1991 to 2020. And the data came in a continuous form, and we were only interested in the precipitation at the well locations. So we're able to extract this value from ArcGIS using zonal statistic table, and then we had to impute the continuous data from the prism and our well locations, and this gave us the precipitation data at the well locations. And after that, because of the nature of the coastline, we had to create another reference line where we can take our coastal distance from the well from. So we had to create a feature class and use a polyline to create a new reference point that is close enough to the coastal line. And from there, we use the near feature on ArcGIS to get the perpendicular distance from this coastal line from this new created coastal line to our wells. So this gave us the shortest perpendicular distance in units decimals, and we later on had to convert that to miles to make use in our data. So I'll be handing over to Ademola to continue.
Hi, my name is Ademola. So a significant part of our independent variables in developing our models we derive from soil data, and to obtain soil data we went into the National Reserve Conservation Service database to get data sets on Gulf Coast 12 and 13, which were merged and intersected, and then using inputs of well data and soil data, we were able to obtain relevant data for our independent variables. We considered using fishnet ID as one of our parameters, and this fishnet ID was supposed to help spread the well as evenly as possible across the Gulf Coast Aquifer area. Each of those grids were assigned an ID. As I said, soil characteristics form a significant part of our independent variables, and this slide over here is showing the independent variables that we considered, all our independent variables that were considered for modeling our linear and logistic regression. We computed a correlation matrix, and to visualize the correlation matrix, we drew a heat map to show collinearity between all of our parameters, and we use this to guide our decision to drop parameters that we consider highly correlated. Using variance inflation factor, we computed values or factors to show the amount of multicollinearity between our parameters, and we using a literature or study that we've done earlier, we determined that VIF factors that are higher than 10 constitute high problem of multicollinearity. Yeah, I'm going to continue.
Okay, so to fit our model, what we had to do was to split our data set into two categories, which was the training data set and the testing data set. We used the training data set to train our models to understand how our parameters affect our dependent variables, which is the average nitrate value. And then we used the data set to check how our model performed in determining that average nitrate data value. And after that, we were able to come up with a program for the linear regression model. And this is just a preliminary program. We just throw in all our parameters to see how the model reacts to these data and see what happens. And from what we can see here, we can see that from the right, we can see that some of our parameters are confidence interval between negative and positive, which basically means that it is inversely proportional and directly proportional at the same time, which doesn't make any sense. And also for our p-values that are above 0.05, it basically says that our parameters are not statistically significant, so we have to work on that. And after that, I was able to pick out 5 parameters that I felt were going to give me the best values, and I used precipitation, well depth, distance from coast, slope, and soil drain. And from what we can see that many of the confidence interval for our model became stable, because we had some of our parameters that are inversely proportional remain inversely proportional, and the ones that are directly proportional still are still the same. And the p-value for all our parameters kept under 0.05, so which is a good thing. After that, we had to create a threshold and separate our data into 2 separate bins, which is we had to create a threshold of 10 milligrams per liter per liter of nitrogen. For average nitrogen below 3 milligrams, we put that in the bin of 0, and For the average nitrogen above 3, we had to put that in a bin of 1, and then we tested our model and see how it performed with the training data set, and we did the same thing again with the testing data set, and we can see how the model performed. And after that, we also had to, using start model package, we had to check for the heteroskedasticity of the model, the homoskedasticity, and the normality of the model using the p-value if it is above 0.05. So basically, that is just what this is showing us here. That was for the linear regression. For the logistic regression, I used the exact same values to fit in my model for the logistic regression, and this is the confusion matrix that I got from that. And also, this is the ROC curve, which basically is the receiver's operative characteristic. It is a correlation between the sensitivity and the specificity of our data. And we also have our accuracy, precision, and recall of our model for the training data set and test data sets. So from here, I'll be handing over to Ademola to explain his model.
Designed using the guidance of our multicollinearity. I selected precipitation, perviousness, distance from coast, slope, and drain as parameters that help to obtain values, p-values that are less than 0.05, and also to be able to have consistently positive or consistently negative correlation intervals. So the model shows for the training data that the true positive values for the training data were good, and the true negative values also were high. The aim of basically using the guidance of multicollinearity again is to be able to limit or to minimize the false negative values as much as possible. For the linear regression using the same parameters, I was able to obtain results of the confusion matrix to summarize. I used the confusion matrix to summarize the performance of the model, and the summary here shows that between my training and testing models, there is a reduction of the false negative predictions. The ROC curve here shows that the model is better than random guessing using the AUC numbers, which is close to 1 or higher than 0.5. And for the testing data, there is an improvement from 85% to the accuracy between the training and the testing data goes from 81% to 83%. The precision goes from 69 to 70, and the recall goes from 63 to 65%.
So this is our model 5. This is created using linear regression model and using world depth, precipitation, distance from coast, and organic matter content as 4 parameters to predict the amount of nitrate. So as we can see, none of the confidence interval includes 0, and all the parameters that are used here is showing p-value less than 0.05, so they are statistically significant. But still, there's a value of conditional number, high conditional numbers, showing that there's a chance of multicollinearity being present still in the model. So the result, as we can see here, is we have done the test for heteroscedasticity, normality, and autocorrelation. So the null hypothesis of the heteroscedasticity is if the p-value is less than 0.05, we reject the null hypothesis. So we have the evidence of heteroscedasticity in the model. Similarly, we can conclude that there are residuals do not follow the normal distribution, and also that there is not enough evidence to conclude that there is autocorrelation as well in the residuals. And this was the result we got. We see there are very less false negative. That shows that people will not accidentally drink the water that is infected. That is a good thing, instead of having high value in here. So to summarize our project, we predicted average nitrate using linear and logistic regression model. Precipitation, well depth, and distance from coast were the most used parameters throughout all of our models, and logistic regression model was doing better to predict the true state of the well, saying if the true values were more on that. And then linear regression was showing very low number of false positive when compared to the logistic regression.